Night. The bottom of the Grand Canyon. You can't see the walls, but you can feel them. A mile of rock on either side, rising straight up into a sky so full of stars it almost hurts. Somewhere below your feet, the Colorado River murmurs. It sounds patient. It sounds like it has nowhere to be. Then a crack. A deep, rolling crack, like thunder that starts inside the earth. A slab of limestone has let go of the wall. Hundreds of tons of rock falling through the dark. The echo rolls through the gorge for 10 seconds, 15, then silence again. The canyon just got a little wider, by an inch, maybe 2. Nobody saw it. That's how almost everything has happened here for the last 5.5 million years. Grand Canyon, 277 miles long, 18 miles across at its widest, more than a mile deep. If you scooped out all the missing rock and tried to fill the hole with every drop of river water on Earth, the canyon would only be 1/3 full. And the river that dug it? By some measures, 1/10 the size of the Mississippi. A modest, muddy desert river, shallow enough to wade in places, narrow enough to throw a stone across. The Mississippi carries many times more water, and it hasn't carved anything. So how did this one do it? Scientists have spent 150 years chasing that question, and the deeper they dig, the stranger the answers become. Because most of the evidence is gone, washed away by the river itself, buried under landslides, scorched by volcanoes. One geologist put it this way: this is a crime scene where almost all the evidence has been washed away. Here's what we do know. Tiny garnets, no bigger than grains of sand, that remember the weight of mountains that vanished over 1 billion years ago. A handful of gravel that proved the entire scientific establishment wrong. A lake bigger than Lake Michigan that once sat right here, grew too full and spilled over the edge, and that single overflow may have started the whole thing. Lava that poured into the canyon and tried to stop the river. The river won, every time. And people. People who built stone rooms on cliff faces 800 feet above the water, stored corn in them, and then one day, around the year 1200, left. All of them, and never came back. To understand how the river pulled this off, we need to start with what was here before it, long before it, nearly 2 billion years ago. 1.7 billion years ago, this place looked nothing like what you see today. The desert didn't exist. The river didn't exist. Even North America didn't have the shape you'd recognize. What stood here was a mountain range, and it was enormous. We know this because of Carl Karlstrom. Karlstrom is a geologist who has spent decades on the Colorado River, following the same route that John Wesley Powell ran in 1869. Powell was the first person to take boats through the canyon. He was a Civil War veteran who had lost his right arm at the Battle of Shiloh, and he led 9 men in 4 wooden boats into a gorge that no one from the outside world had ever mapped. When they reached the bottom, where the oldest rocks in the canyon rise up from the riverbed, Powell wrote about them in his journal. He called them ugly black rocks. He hated them, and for a practical reason. These dark, twisted walls created the worst rapids on the river. They nearly capsized his boats. Karlstrom loves those same rocks. He calls them a bonanza, because inside the black stone, there's a record. The rocks are called the Vishnu Basement, and they are 1.7 billion years old, less than half the age of the Earth, but old enough that when they formed, the most complex life on the planet was a single cell. The oceans held nothing bigger than bacteria. If you had stood here, you wouldn't have seen a single living thing without a microscope. But age alone doesn't make them special. What makes them special is what they remember. Look at the Vishnu rocks under a microscope, and you'll find tiny crystals, garnets, each one smaller than a grain of sand. And each one holds a chemical clue. The more calcium a garnet contains, the greater the pressure it formed under, which means the more rock was piled on top of it when it crystallized. Think of the garnet as a kind of black box, like the flight recorder on an airplane. The airplane is gone, the wreckage has been cleared away, but the black box survived, and the data is still inside. When Karlstrom's team measured the calcium in those garnets, the numbers told a clear story. These rocks had once been buried 6 miles beneath the surface. 6 miles of solid stone pressing down. That's the weight of mountains as tall as the Himalayas. Try to picture that. You're standing on the canyon floor, looking up at these dark, crumpled walls. The river is at your feet. The rim is a mile above your head. And 1.7 billion years ago, this same spot was buried under a mountain range that reached into the upper atmosphere. Where did those mountains come from? Plate tectonics. Around 1.7 billion years ago, a chain of volcanic islands was drifting across the ocean toward the edge of the ancient North American continent. When they collided, it was slow, but the force was beyond anything we see today. Imagine a long freight train hitting a wall. Each car crushes into the one ahead. The metal buckles, folds, rises. That's what happened here, except the cars were volcanic islands, and the metal was the Earth's crust. The islands folded into each other, crumpled, and piled up into a mountain range, the Vishnu Mountains. For a while, they were among the tallest things on the planet, and then they weren't. Erosion works slowly, but it never stops. Rain falls and runs downhill. Frost cracks open seams in the rock. Wind carries away the dust. Over the next 500 million years, the Vishnu Mountains wore down. Not in a catastrophe, not in a collapse, but grain by grain, century by century, until the peaks flattened to a plain. 500 million years of the tallest mountains on Earth reduced to a smooth, low surface barely above sea level. Everything above was gone. Everything except the roots. The black rocks at the bottom of the canyon are those roots. They are the stumps of mountains that stood here when life on Earth was still learning to divide into 2 cells. And inside them, the garnets still hold the data. They still remember the pressure, still carry the imprint of how much rock used to be above them. One way to feel the scale of this: if you took all of Earth's history, 4.5 billion years, and squeezed it into a single calendar year, the Vishnu Mountains would appear sometime in mid-August. They would wear down by late September. Dinosaurs wouldn't show up until mid-December, and they'd be gone by the 26th. All of recorded human history, every war, every empire, every city, every book, every song, fits into the last 35 seconds before midnight on December 31st. The garnets have been waiting since August. So the canyon is a library, but it's not a tidy one. It's a library where most of the books have been destroyed. and the surviving pages are out of order, and you need a chemistry lab and a microscope just to read them. The garnets are one page. They tell us what used to stand here. They tell us that the story of the Grand Canyon doesn't begin with a river cutting downward. It begins with mountains rising up, and then disappearing so completely that for 1 billion years there was no sign they had ever existed. The mountains vanished. A flat plain remained. No gorge, no river, nothing that hints at the future canyon. But that plain won't stay empty for long, because the sea is already on its way. A seashell. An ordinary seashell, the kind you'd pick up on a beach and put in your pocket without thinking. Except this one is locked inside a rock wall at an elevation of more than 1 mile above sea level, 300 miles from the nearest ocean. It's been there for about 270 million years. How does a seashell end up in the desert, 1 mile up in the sky? The answer is that the desert came later. For most of the last 1 billion years, this place was underwater. The sea came in and went out again, came in and went out, at least 8 separate times. 8 different oceans spread across hundreds of millions of years, and each one left something behind. When a sea covers the land, it drops sediment. Sand settles first, quickly, and over millions of years, the weight of newer layers presses it into pale sandstone. Mud drifts down more slowly and becomes shale, which is dark. Shells and coral skeletons dissolve into a calcium-rich paste that hardens into limestone. And the red that you see in postcards of the Grand Canyon, that deep rust color, that's iron. Tiny amounts of iron trapped inside the stone, slowly reacting with oxygen over millions of years. The same process that turns a nail orange if you leave it out in the rain. Except this rusting took 60 or 70 million years to finish. So when you look at the canyon wall, you're looking at a stack of these layers. Light sandstone, dark shale, white limestone, red iron-stained rock. Each layer records a separate period of the Earth's history, written in its own kind of stone. And the order matters. The deeper you go, the older the rock. Walking down from the rim to the river is walking backward through time. Every step takes you further into the past, until you reach the black Vishnu rocks at the bottom, where the clock reads 1.7 billion years. Carl Karlstrom, who has mapped these layers over decades of fieldwork, describes the canyon as the most complete geological record exposed anywhere on Earth. You can find older rocks in other places and thicker layers elsewhere. But almost nowhere else can you see so many different periods of Earth's history stacked on top of each other, cut open, and lit by the sun. The seas brought more than mud and sand. They brought life. In the Kaibab limestone, the canyon's top layer, about 270 million years old, you can find the remains of mollusks, corals, and brachiopods, those small-shelled creatures that looked a bit like clams, but weren't related to them at all. This was a shallow, warm sea, something like the coast of modern-day Florida. Creatures lived and died here by the billions, and their shells piled up on the bottom, layer after layer, until the whole mass hardened into the white cap of rock that tourists stand on today when they look over the railing at the south rim. And deeper in time, the seas got stranger. In the Cretaceous Age rocks of the Colorado Plateau, near the canyon, Paleontologist David Gillette found the skeleton of a plesiosaur, a marine reptile with a long neck and paddle-shaped limbs that hunted these warm waters about 90 million years ago. Gillette called it a once-in-a-lifetime find. The creature had been swimming in a tropical ocean right here, in a place that is now bone-dry and 7,000 feet above sea level. Sharks swam here, alongside turtles and coiled ammonites, those spiral-shelled relatives of the octopus, some as wide as truck tires. This region wasn't a desert at the edge of a continent. It was a seabed at the center of a warm, shallow ocean that covered much of what is now the western United States. There's a simple way to picture how the layers formed. Take a tall glass jar. Fill it halfway with water. Drop in a handful of sand mixed with clay and a few crushed shells. Shake it hard, then set it down and watch. The heavy sand grains fall first. The fine clay drifts down slowly, settling on top. The lightest shell fragments come last. You've just made a tiny version of what happens when a sea floods the land and then retreats. That's one cycle, one layer. Now imagine doing that dozens of times, over hundreds of millions of years. Every time the jar settles, a different ocean has come and gone, leaving its own stripe of color in the glass. And here's what's easy to miss about the scale. Some of these layers are only a few meters thick. You can reach out your arms and touch the top and bottom of a single band of rock. But that band holds the entire life and death of an ocean. Millions of years of waves, tides, storms, creatures being born and dying, compressed into a distance you could step across in 2 seconds. Time, in the canyon, is almost physically heavy. You can feel how much of it is packed into every wall. The last sea withdrew from this region roughly 80 million years ago. What it left behind was a low, flat plain, barely above water level. A quiet, dull landscape with nothing to suggest what was coming. There was still no canyon and no river, just a plain made of old seabeds stacked one on top of another like pages in a closed book. But think about where we're standing. More than a mile above the ocean. Mollusk shells, plesiosaur bones, the floors of tropical seas, all of it sitting at the altitude of a mountain pass. The ocean floor ended up in the sky. And that raises a question that puzzled geologists for over a century. How did all of this get lifted so high? So how does a shell that lived on the ocean floor end up at 7,000 feet? The short answer? The floor moved. The whole floor, thousands of square miles of it, lifted straight up with everything on top still in place. To understand how that's possible, you need to know one thing about the Earth that people didn't figure out until the 1960s. Picture the surface of the Earth not as one solid shell, but as a dozen huge pieces of eggshell floating on something hot and soft underneath. Those pieces, called tectonic plates, drift. Slowly, a few centimeters a year, about the speed your fingernails grow. And when two pieces collide, one of them slides under the other. The heavy one goes down, the lighter one rides up. Along the line where they meet, the Earth crumples. That's how most mountain ranges are built. The Himalayas, for example, formed when the plate carrying India crashed into Asia. The collision zone buckled under the pressure, and the rock was pushed skyward. The Alps, the Andes, the Urals, same basic story. Two plates meet. The ground between them gets crushed and forced up. About 130 million years ago, the same thing began happening along the western edge of North America. A slab of heavy ocean floor, made mostly of a dense volcanic rock called basalt, began sliding under the lighter rock of the continent, the way a heavy card slides under a lighter one when you push two cards together on a table. As the ocean floor went down, the continent above it rose. The collision was pushing up the Rockies to the north and the Mogollon Highlands to the south, and the entire western half of the continent was slowly rising. You'd expect the same thing to happen here, and it did, partly. When plates collide, the usual result is a mess. The ground folds and tilts and cracks apart. Layers that used to be flat end up bent at steep angles or flipped upside down. If you visit the Canadian Rockies, you can see ancient seabeds standing almost vertical, tilted 90 degrees from where it started. That's normal for a collision zone. What happened at the Colorado Plateau was different. The layers stayed flat. All of them rose together, keeping their original order. Imagine you're standing in an elevator on the ground floor of a very tall building. The elevator starts to move. It rises one floor, then 5, then 20. You don't feel the motion because it's perfectly smooth. And when the doors open at the top, everything inside the elevator is exactly where it was when you stepped in. The floor didn't tilt. Your coffee didn't spill. That's what the Earth did to this part of North America. The event is called the Laramide orogeny, that is, the Laramide mountain building event, named after a mountain range in Wyoming. It began roughly 70 million years ago, and it went on for millions of years. The flat seabed, with all its layers of sandstone and shale and limestone still stacked neatly on top of each other, rose gradually to an elevation of about 7,000 feet. The water drained off to the northeast. What remained was a flat, dry, high surface, the Colorado Plateau. And that's why the Grand Canyon looks the way it does. That's why, when you stand at the rim and look across, the layers in the opposite wall are perfectly horizontal, like the stripes on a flag. They haven't been bent or broken by the uplift, because the uplift was even. The whole plateau went up together, like a tabletop being raised on a jack. A cake lifted out of the oven, still level, every layer intact. The speed of this was almost comically slow. Millimeters per century. In a single human lifetime, you wouldn't notice anything had changed. Your grandchildren wouldn't notice. 100 generations of your family could live and die on this plateau, and the total rise during that time would be less than the thickness of a coin. But give the process 70 million years, and the ground moves 1.5 miles. John Spencer, a geologist at the Arizona Geological Survey, has spent years studying the timing and mechanics of this uplift. And he's careful to point out that the picture is messier than it sounds. Some geologists believe the plateau reached its current height in one long, steady rise that began 70 million years ago. Others argue that there was a second, more recent push, around 6 million years ago, that gave the plateau an extra boost. Spencer is skeptical of that idea. "I don't believe in tectonic jumps," he says. The debate hasn't been settled, and it may not be settled soon, because the evidence is buried under the very rock it's supposed to explain. What everyone agrees on is the result. By somewhere between 70 and 6 million years ago, depending on whose model you trust, the Colorado Plateau stood at roughly its present height, 7,000 feet above the sea. A high, flat stage made of layered rock, waiting. But there was still no canyon. The plateau had its layers, its elevation, its steep western edge where the land dropped sharply toward the lower desert. Rivers ran across its surface, draining off the mountains to the east. Rain fell and ran off. Streams carved shallow valleys. The stage was ready. What was missing was the leading actor. The river that would cut through all those layers, all the way down to the black roots of the Vishnu Mountains, and open up 2 billion years of Earth's history in a single wound. Scientists thought they knew which river it was and when it arrived. For decades, the answer seemed settled. And then, a 24-year-old graduate student, sent out on a routine field check, looked at the ground and saw something that no one had noticed before. What he found overturned 50 years of accepted science. If you're enjoying this journey through 2 billion years of rock, I'd really appreciate it if you hit the like button. It helps more people find this film. And if you haven't yet, consider subscribing to the channel. Quick question for you. The entire Colorado Plateau was lifted a mile into the sky without tilting a single layer. If you could witness any one geological event from Earth's past with your own eyes, which one would you choose? Let me know in the comments. You try to believe what your professors tell you, but what you see in the field is telling you something strange. Richard Young said that years later, looking back on a moment in 1969 that changed the course of his career and, eventually, the course of an entire science. He was 24 years old, a graduate student, and he'd been sent to do a simple job. At the time, the question of when the Grand Canyon formed seemed settled. Scientists were confident they had the answer, and the answer was about 50 million years ago. The evidence came from a place called Hindu Canyon, an ancient riverbed carved into the plateau long before the modern Colorado River existed. The rocks in Hindu Canyon were around 50 million years old. The logic ran like this. If this old riverbed was the ancestor of the Grand Canyon, then the canyon itself must be at least that old. 50 million years. Tidy and widely accepted. It appeared in textbooks. Nobody seriously questioned it. Young's assignment was routine. Go to Hindu Canyon, examine the old riverbed, and confirm what the existing science already said. Graduate students get sent on jobs like this all the time. The idea is that you learn field methods by checking work that's already been done. You're not expected to discover anything new. You're expected to come back and say, yes, the theory holds. Young went to Hindu Canyon. He knelt down at the riverbed, and he looked at the gravel. Here's something most people don't know about river stones. When water moves over a bed of loose rocks, it pushes them into a particular position. The stones settle with their flat sides tilted slightly upstream, leaning into the current, the way shingles on a roof overlap toward the sky so rain runs off. Once the river dries up or the sediment hardens, the stones stay frozen in that position. Millions of years later, you can still read which direction the water was flowing, just from the angle of the gravel. Every pebble is a tiny compass needle, locked in place by the current that moved it. Young looked at the gravel in Hindu Canyon and saw that the stones were leaning the wrong way. The water hadn't flowed southwest toward the Pacific, the direction the Colorado River runs today. It had flowed northeast, away from the canyon and away from the sea. He checked again, and again. The pebbles were clear. The river that had carved Hindu Canyon was a completely different river, flowing in the opposite direction. It had nothing to do with the Colorado, which meant it had nothing to do with the Grand Canyon. Think about what that meant for a 24-year-old at the start of his career. The accepted age of the Grand Canyon, the number in every textbook, the figure his own professors taught, was based on the assumption that Hindu Canyon was carved by an ancestor of the Colorado River. Young had just pulled that assumption out from under the whole structure. If Hindu Canyon's river flowed northeast, then it wasn't the Colorado's ancestor. And if it wasn't the ancestor, then the 50-million-year age was wrong. The canyon could be much younger, but how much younger? The answer came from a different place entirely. Muddy Creek, near the western end of the Grand Canyon, close to what is now Lake Mead. For millions of years, a calm freshwater lake sat in this basin. Clean water, no sediment. Tiny mollusks lived in it. Their shells dissolved into the lake bed and formed a thick layer of freshwater limestone, smooth and white. And then, about 5.5 million years ago, the limestone stops, abruptly. One layer is clean white stone. The next is dark, muddy sediment, full of sand and silt, carried from hundreds of miles upstream. Something had changed. A river had arrived, dumping enormous amounts of debris into the lake. The clean water turned cloudy. The mollusks couldn't survive in it. The limestone stopped forming. That river was the Colorado, and the moment it arrived at Muddy Creek is, as far as geologists can tell, the moment the Grand Canyon began. The lake's death certificate is the canyon's birth certificate. 5.5 million years. That was the new number. 10 times younger than the old one. The canyon wasn't an ancient monument that had been sitting here since the age of dinosaurs. In geological terms, it was practically brand new. Now, scientists still argue about the exact date. Some evidence, based on tiny marine fossils called foraminifera found in the lower Colorado, suggests the river may have been flowing along its present course as early as 4.5 million years ago. The difference between 4.5 and 5.5 million years might not sound like much, but in the world of geology, 1 million years is a serious gap, and it points to a deeper disagreement about how the canyon was carved. What everyone agrees on, though, is the basic picture. The Grand Canyon is young, far younger than anyone had believed before 1969. And Richard Young, the grad student who knelt at a riverbed and read the pebbles the way you'd read a compass, was the one who cracked it open. He didn't set out to overturn a theory. He was sent to confirm one. But the ground told him something his professors hadn't expected, and he trusted what he saw more than what he'd been taught. That takes a certain kind of courage. When you're 24 and your career hasn't started yet, disagreeing with the people who control your future is not a small thing. Young did it anyway, and the science moved. But his discovery, satisfying as it was, opened a harder question. If the canyon is only 5 or 6 million years old, then the river had far less time to do its work than anyone had thought. The Colorado carries a fraction of the water the Mississippi does, and the Mississippi, for all its power, has never cut anything close to a canyon. So how did a smaller, weaker river manage to cut through a mile of solid rock in what amounts to a geological instant? One geologist in Phoenix decided to find out. And his method was unusual. He built a canyon with his own hands. A community college campus in Phoenix, Arizona. Not a famous research university. Paradise Valley Community College. In the parking lot behind the science building Somebody has piled several tons of dirt into the shape of a small plateau, maybe waist-high, a few meters across. Garden hoses lie coiled at the edges. And a man named John Douglas is standing there with a hose in his hand, running water over the dirt, watching what happens. Douglas is a geography professor. He's been teaching here for years, and he has spent most of his adult life thinking about one question: how did the Grand Canyon form? "I learned early on that we didn't understand how the Grand Canyon formed," he once said, "and I decided to spend most of my life on it." His idea is simple. So simple, it almost sounds too easy. He calls it the spillover theory, and it goes like this. A river flows across the plateau and runs into a low basin, a natural bowl in the landscape. The water has nowhere to go, so it collects. A lake forms. The lake grows. Year after year, century after century, the water level rises. And then, one day, the lake reaches the rim of the basin and spills over the edge. At first, it's just a trickle, water running down the far side of the rim, following the steepest path. But moving water picks up speed on a slope, and the faster it moves, the more rock it can carry away. The trickle cuts a notch. The notch deepens into a channel, and the channel opens into a gorge. And once the process starts, it feeds itself. The deeper the cut, the steeper the drop. The faster the water, the more rock it tears loose. The canyon doesn't grow slowly. It runs away with itself. On the dirt model in the parking lot, Douglas could watch all of this happen in a few minutes. He'd fill the basin with his garden hose, and when the water spilled over the rim, it would carve a miniature canyon in the side of the dirt plateau, fast and forceful, feeding on its own momentum. "Imagine you went into your backyard," he told an interviewer, "dug a hole, and filled it with a garden hose. The water fills the hole, spills over the edge, and carves a little canyon in the wall." That's essentially all that happened. But a model made of dirt is just a demonstration. To prove that the real canyon formed this way, Douglas needed a real lake. A lake large enough and old enough to have existed before the canyon itself. And it needed to be in the right place, east of the canyon, upstream, where the Colorado River could have fed it. The lake exists, or rather, it existed. About 100 miles east of the Grand Canyon, in northeastern Arizona, geologists have found the remains of a body of water called Lake Bidahochi. The evidence is in the sediments, layers of green clay, the kind that forms only in deep, still water with very little oxygen at the bottom. Classic evidence of a big lake. Freshwater fossils in the same sediments date to roughly 6 million years ago, which makes the lake older than the canyon. By some estimates, based on the contour lines of the surrounding terrain, the lake may have covered up to 20,000 square miles and held more than 3,000 cubic miles of water. To put that in familiar terms, that's comparable in size to Lake Michigan. If such a lake had spilled over the edge of the plateau, the resulting flood would have been the largest in the history of the continent. But those numbers come with a warning. They appear in documentaries and popular accounts, but some geologists, including William Dickinson, have argued that Lake Bidahochi wasn't a single giant lake at all. It may have been a series of shallow, seasonal lakes, what geologists call a playa system, much smaller than the Michigan-sized body of water described in the films. The April 2026 paper doesn't settle the size question. What it does settle, or comes close to settling, is something else. In April 2026, the journal Science published a paper by He, Crow, Douglas, and their colleagues. The team analyzed roughly 3,600 tiny crystals of zircon, a mineral that forms in volcanic rock and gets carried downstream by rivers. Every zircon crystal carries a chemical signature, a ratio of uranium to lead, that acts like a fingerprint. It tells you where the crystal came from. The team extracted zircon from the Bitahoche Basin sediments. Then they compared the fingerprints to known rock formations hundreds of miles upstream. The match was clear. By about 6.6 million years ago, zircon from the Browns Park Formation, a rock unit in Utah and Colorado, hundreds of miles upstream, was showing up in the Bitahoche Basin. At the same time, the rate of sediment building up in the basin jumped by a factor of 10. The Colorado River had arrived. It was pouring its load into the basin, and once the basin filled, the water had only one way to go: over the rim. John Douglas is a co-author on that paper. His co-authors include scientists from the United States Geological Survey and the University of California. From a garden hose model made of dirt on a community college campus to a paper in one of the most respected scientific journals in the world. 25 years. Ryan Crow, one of the USGS researchers on the team, put it plainly. "I think lake spillover is the most likely mechanism." But Douglas is careful. He doesn't claim total certainty, and neither does the paper. There are other ideas about how the canyon started. One of them is headward erosion, the idea that a waterfall at the western edge of the plateau slowly ate its way backward upstream, cutting into the plateau from the outside in. Christine McDougall, a geologist working on the lower Colorado, found tiny fossils called foraminifera, so small that 100 of them would fit on a single grain of salt in rocks near the river's mouth. Those fossils suggest the river was already flowing along something close to its modern path as early as 4.5 million years ago, which would support a different timing for the canyon's origin. Other geologists have pushed back using a chemical signal in the rock called strontium isotopes that can tell freshwater from seawater. Their readings, they argue, don't support headward erosion at all. The debate continues. "We'll never know for sure," Douglas says, "unless somebody builds a time machine." That's honest science. The best explanation we have today, held with open hands and ready to be revised if something better turns up. That's how this works. What the spillover theory does answer, at least partly, is the question that's been open since the canyon turned out to be young. How did a modest river do all this in 5 or 6 million years? The answer, or part of it, maybe it wasn't so modest at the start. Maybe it began as a catastrophe, a lake the size of a small sea going over the edge, tearing open the first wound in the rock. After that, the river only had to keep going. But keep going is the hard part. The lake gave the river its start. A start is not a finish. The canyon needed to grow deeper and wider for another 5 million years. How fast was that happening? How do you even measure the speed of a river cutting through stone? One geomorphologist figured out a way, but to get his answer, he had to work in total darkness. Dawn on the Arizona Strip. If you haven't heard of it, that's the point. This is one of the most isolated stretches of land in the lower 48 states, a wide, dry plain north of the canyon, cut off from the rest of Arizona by the gorge itself. Almost nobody lives here. The silence in the morning is so complete, you can hear your own breathing. On the canyon rim, the rock changes. Small, cone-shaped mounds dot the edge, some barely taller than a person, others the size of a small hill. And running down both canyon walls, from the rim toward the river far below, there are black tongues of stone. They look like frozen rivers, and that's exactly what they are. Lava. This is where Joel Peterson comes to answer a question that sounds almost absurdly simple. How fast is the canyon getting deeper? Peterson is a geomorphologist, that is, a scientist who studies how landscapes change shape over time. And his method depends on darkness. Certain minerals in river sand, mostly quartz and a mineral called feldspar, absorb energy from the natural radiation in the rock around them. The longer these grains sit buried in the dark, the more energy they store. When you finally expose them to light, they release that stored energy as a faint glow. The brighter the glow, the longer the sand was buried. It's a clock built into every grain. The catch is that the clock resets the instant the mineral sees sunlight. So Peterson has to be careful. He drives a hollow metal tube into a sandy bluff along the riverbank. The tube goes in sealed and comes out sealed. He wraps it in foil. Back in the lab, in a room with no windows and no light, he opens the tube, extracts the sand, and bombards it with radiation. The grains glow. The glow tells him when this sand was last at the surface, which tells him when the river was flowing at this level. By comparing samples from different heights along the canyon wall, Peterson built a timeline of the river's descent. The result? The Colorado cuts downward at roughly 1,000 feet per million years, a little more than an inch per century. In a single human lifetime, the canyon deepens by less than the width of a pencil lead. You'd never see it happen. But give that process 5 million years, and the river carves more than a mile of solid rock. Now here's the answer to a question that's been hanging over this whole story. The Mississippi carries many times more water than the Colorado, and yet the Mississippi has never carved a canyon. Why? Because canyon carving isn't about volume, it's about slope. The Colorado River drops about 8 feet for every mile it flows through the canyon. That sounds gentle, barely a step down. But the lower Mississippi drops only about 6 inches per mile, which is nearly flat. The Colorado's gradient, that is, its steepness, is 15 times greater. And the river doesn't cut rock with water alone. It cuts with tools, boulders, cobbles, sand, all of it tumbling along the bottom, hammering the bedrock like a belt sander made of stone. Before the Glen Canyon Dam was completed in 1963, the Colorado carried close to 500,000 tons of sediment every day, 5 tons per second. All of that rock grinding against the bottom, hour after hour, year after year. Think of it this way. A loaded freight truck on a flat highway has a lot of weight, but it's barely moving downhill. A skier on a steep slope weighs almost nothing, but gravity pulls them fast, and every bump they hit tears up snow. The Mississippi is the truck. The Colorado is the skier. Less weight, but far more speed. And speed is what cuts. And then the volcanoes arrived. The Uinkaret volcanic field sits on the canyon's north rim. Over the last 2 million years, more than 150 lava flows have poured from over 200 cinder cones along this stretch of the canyon. Molten rock spilled over the rim and ran down the walls, a mile straight down, crashing into the river below. Picture it, liquid rock, glowing orange, hitting ice-cold river water. The steam clouds must have been visible for miles. At least 13 of these lava flows were large enough to dam the Colorado completely. Walls of hardened basalt, some 800 feet tall, some as tall as 2,000 feet, blocking the entire width of the gorge. The river stopped. Water pooled behind the dam and formed a lake. The largest of these lava-dammed lakes was 2,000 feet deep and stretched back into what is now Utah. But the river is patient. Water rises behind the dam, pressure builds, the dam cracks, and when it fails all at once. Every lava dam the canyon has ever seen has been destroyed by the river behind it. 13 dams built, 13 dams broken. The river won every single round. And the volcanoes may not be done. Vulcan's throne, a cinder cone perched on the north rim, is only about 73,000 years old. It sits 4 miles from Lava Falls, the most powerful rapid on the Colorado. And just to the south, the Little Springs lava flow is dated to roughly 1,000 years ago. Pottery fragments made by Pueblo people were found embedded in its lava. People were living nearby the last time the earth opened up here. Geologists believe it could happen again. The canyon is also growing wider, right now, by a different process. Rain soaks into the soft shale layers and weakens them. The shale washes out, and when enough of it is gone, the hard limestone layer above loses its support and breaks off in enormous slabs. One geologist who has spent hundreds of nights camping on the canyon floor described it this way: "I've heard maybe 1 or 2 rocks fall in all that time, but when it happens, it's instant. You hear a crack, and then a roar that echoes for 10 seconds. By morning, a wall that had been there for 1,000 years is gone. An inch per century. In 5 million years, that inch becomes a mile. Water and lava and rockfall all play their part, but the real force behind all of them is time. Time, and the fact that it never stops. The river created this world. It carved a space in the rock where springs could seep out of the walls and cottonwood trees could take root along the banks. Wildflowers bloom in the narrow strips of sunlight that reach the canyon floor. A world within a world, sheltered and hidden thousands of feet below the desert above. And people found it. Thousands of years ago, people climbed down into this gorge, saw what the river had made, and decided to stay. They built homes, grew corn, and stored food in stone rooms on cliff faces so steep you'd need a rope to reach them. And then, one day, around the year 1200, they left, all of them, and they never came back. Until now, this story has been measured in millions and billions of years. Rocks, rivers, volcanoes, the slow grind of a continent. But the canyon is also a human record. People have lived here. And once you start measuring time by human lives instead of by layers of stone, the scale changes. 1,000 years stops feeling ancient. It feels like yesterday. People reached the canyon at least 10,000 years ago, possibly 13,000. We know because they left spear points behind. Stone blades shaped for hunting large animals. The kind of tools that Paleo-Indian people carried across the continent at the end of the last ice age. For thousands of years after that, nomads and hunters moved through the canyon, following water and game. And then, someone started making strange little objects. In caves scattered through the canyon, archaeologists have found hundreds of tiny figurines. Deer, bighorn sheep, carefully shaped from split twigs and bent into lifelike poses. Some of them have small spears pushed through their sides. They're old, between 4,400 and 3,100 years. Who made them and why, we have no idea. Were they hunting charms, meant to bring luck before a hunt? Offerings placed in caves as gifts to the underworld? There are no written records, no oral traditions that explain them clearly. 1,300 years of people making these figurines, leaving them in the dark, and walking away. Whatever the purpose was, it's been lost. Then, around the year 1050, something shifted. A group called the Ancestral Puebloans, ancestors of today's Hopi and Zuni people, moved into the canyon and began to settle. They chose spots near the river, where small deltas of fertile soil collected at the mouths of side streams, and they planted crops. The population grew. Within a century or so, the inner canyon was home to a real community, with dwellings, farming, and trade. But they did something unusual with their food. Instead of storing grain near the fields where they grew it, they carried it 800 feet straight up to ledges so narrow and exposed that reaching them required climbing trails cut into the rock face. There, on those inaccessible shelves, they built tiny granaries, stone chambers no bigger than a closet, sealed with mortar. In the 1960s, when archaeologists finally reached some of these granaries, they found corn cobs still inside. And in the mortar between the stones, the builders' fingerprints were still pressed into the surface, perfectly preserved after 900 years. Why store your food so far from where you live? Why haul sacks of grain up a near vertical climb? The answer, almost certainly, is fear. The same pattern of high, hidden storage appears across the entire American Southwest during this period. People were hiding their supplies, and the most likely threat was other people. By the late 1100s, the community in the canyon was gone, and the canyon wasn't alone. Across the entire Southwest, populations collapsed. Drought played a part. Tree ring records show a severe dry period in the late 1200s. Trade networks fell apart. Construction shifted from open villages to defensive positions on cliff edges and in alcoves, as if everyone were preparing for attack. The Paiute people later told John Wesley Powell that their name for one stretch of the canyon, Nankip, means where the Indians fought. The memory of that conflict survived in the name of the place itself, passed down through generations. But the people didn't vanish. They moved. The Hopi, the Zuni, and other Pueblo peoples trace their ancestry to these same ancestral Puebloans. For the Zuni, the canyon holds a meaning that goes far beyond history. A Zuni elder named Clifford once put it simply, "We all emerged from the bottom of the canyon." In Zuni tradition, this is Sipapuni, the place where the first people came up from the underworld onto the surface of the earth. The canyon is sacred ground, and the Havasupai, a people who have lived in a side canyon called Havasu for more than 700 years, are still there. Supai Village sits on the canyon floor, population recorded at 208 in the last reliable census, though the actual number is likely higher. There is no road in. Mail arrives 6 days a week on the backs of mules, the only community in the United States where the Postal Service delivers by pack animal. The nearest post office is about 70 miles away. A permit to hike down and camp near Havasu Falls costs $455 for 3 nights. One Havasupai elder described their bond with the place in a single sentence: "The river is everything in our lives." The canyon also generates myths, and one of them has refused to die for over 100 years. On April 5, 1909, the Arizona Gazette ran an article with a headline that would have stopped anyone mid-coffee. "Explorations in Grand Canyon. Remarkable finds indicate ancient people migrated from Orient." The article described a man named G.E. Kincaid, identified as a Smithsonian explorer, who claimed to have discovered a system of tunnels high in the canyon wall. Inside, according to the report, chambers filled with copper tools, hieroglyphic inscriptions, and preserved remains. The details were startlingly specific, down to room dimensions, corridor layouts, and the types of artifacts found in each chamber. The paper printed it all as fact. And then, silence. There was no follow-up, no expedition, no museum announcement. The story simply disappeared. The Smithsonian denies any connection. Neither Kincaid nor the Professor S.A. Jordan mentioned in the article appears in any institutional archive. And the Egyptian-sounding names that dot the canyon map, Isis Temple, Tower of Ra, Osiris Temple, were given by geologist Clarence Dutton in the 1880s. Dutton had a taste for Eastern mythology, and the names stuck. The area near the alleged cave is restricted to hikers, but the restrictions are there for safety and to protect the ecosystem, not to conceal anything. The Federal Aviation Administration limited flights below the canyon rim starting in the 1980s, but that was because of a 1986 mid-air collision between 2 aircraft, not because of hidden tunnels. So the story falls apart, almost completely, except for one loose thread. Why did the Gazette run such a detailed, specific article and then never mention it again? Was Kincaid a hoaxer? Was it a publicity stunt by the newspaper? Or did he find something real, perhaps not Egyptian at all, perhaps indigenous, that simply went uninvestigated? There is no answer. 95% of the canyon's archaeological sites have never been surveyed. The canyon creates legends because there genuinely is something astonishing hidden inside it, and most of it hasn't been found yet. And then there's a different kind of secret, one that has nothing to do with ancient civilizations or conspiracy theories. This one is documented, measured, and still not fully dealt with. On the south rim, between Maricopa Point and the Powell Memorial, about 2 miles from the spot where millions of tourists gather every year, there's a chain-link fence. Behind it, an empty concrete pad. If you hike the Bright Angel Trail, rangers direct you around the area. And at Horn Creek, a little further below, a sign reads, "Do not drink the water." Under that pad is a mine shaft, dropping vertically into the canyon wall. The Orphan mine. Between 1956 and 1969, nearly 495,000 tons of uranium ore were pulled from this shaft. The uranium fed Cold War nuclear programs. In 1962, Congress specifically passed a law allowing mining beneath national park land. When the mine shut down, nobody cleaned it up. Dissolved uranium began seeping into the Horn Creek drainage, and it continues today. 10 acres of contaminated soil sit within the park boundary. In March 2018, a teenager visiting the museum collections building happened to be carrying a Geiger counter. The readings were high.
When Park Safety Manager Elston Stevenson learned of the situation that June,
what he found made national news. 3 5-gallon buckets of uranium ore sitting in a room where visitors and staff walked past every day. The buckets had been there since roughly the year 2000. 18 years. The National Park Service later said the initial radiation estimates were overstated and the buckets were removed. But they had sat there for nearly 2 decades before anyone noticed. The Orphan mine is now a federal Superfund cleanup site. That is, a site so contaminated that the government has taken direct responsibility for fixing it. Around the broader canyon region, hundreds of abandoned mines remain. On Navajo Nation land alone, more than 500 are still waiting to be cleaned up. In 2012, a 20-year ban on new uranium mining near the canyon was put in place. In 2023, President Biden declared the Baj Nuavjo Ita Kukveni National Monument, which banned mining on roughly 1 million acres around the canyon.
But existing mining claims were kept in place, and the Pinon Plain Mine, formerly known as Canyon Mine, began extracting uranium in December 2023 after the monument was declared. A full picture of how far radioactive groundwater is spread through the canyon still doesn't exist. The canyon holds ancient mysteries, the kind that stir the imagination. But it also holds a legacy that we put there ourselves, and that one is still leaking. People came and went. The canyon stayed. It's older than any civilization or empire, older than any language spoken on this continent, and it isn't finished. Night again. The same walls, the same stars. Somewhere below, the river whispers the way it has for 5.5 million years. The canyon is doing what it always does, growing, 1 inch per century, invisible to anyone who happens to be standing here. So how did a modest river crack open 2 billion years of the Earth's memory? The answer, it turns out, was never about strength. The Colorado isn't a powerful river. It carries far less water than the Mississippi, but it drops steeply, 8 feet for every mile through the canyon, 15 times steeper than the Mississippi's gentle slide across the plains. And it doesn't cut with water. It cuts with the rocks it carries, boulders and sand tumbling along the bottom, grinding the bedrock away like a slow, patient saw. Soft shale washes out. Hard limestone above it loses its support and breaks away in slabs. Rain seeps into the walls and widens them from the sides. Lava tried to stop the river 13 times. The river broke through every dam, and every layer the river exposed is another page of planetary memory. Mountains that haven't existed for 1 billion years. Oceans that came and went 8 times. Creatures that swam here 90 million years ago and left their bones in the rock. And people who farmed on the canyon floor 1,000 years ago and then walked away. But the answer isn't complete, and it probably never will be. The river destroyed its own evidence. The very process that carved the canyon also washed away most of the clues about how it started. Muddy Creek, near the canyon's western end, is one of the few places where traces of the river's arrival still survive. The rest is gone. As one geologist put it, this is a crime scene where almost all the evidence has been washed away. Scientists still argue about how the canyon began. Was it a lake that spilled over the rim? Or did a waterfall eat its way backward into the plateau? Did one river do the work, or several over different periods? The 2026 paper in Science, with its zircon fingerprints from the Bitahoche Basin, is the strongest case yet for the spillover idea. But even the authors of that paper won't call it settled. "We'll never know for sure," John Douglas said, "unless somebody builds a time machine." That's not a failure of science. That's how science works. Every answer opens a new question. And the canyon has always had more questions than answers. One of those questions is still open. Vulcan's throne sits on the canyon's north rim, a dark cinder cone 4 miles from Lava Falls, the most powerful rapid on the river. It's about 73,000 years old, and the Little Springs lava flow, a short distance to the south, is only about 1,000 years old. Pueblo pottery was found embedded in its cooled lava. People were living nearby the last time the ground split open here. Geologists think it could happen again. The canyon is not a monument. It's a process, and the process is still running. And then, a crash in the dark. Stone letting go of stone. A slab of limestone, hundreds of tons, peeling away from the wall and falling through the silence. The echo rolls through the gorge and fades. The canyon just got a little wider, by an inch, maybe 2. In 1,000,000 years, it will be deeper and wider still. If you think this is grand, you haven't seen anything yet. The river whispers, the wind murmurs. 2 billion years of memory written in stone, and the book is still open. Nobody will ever finish reading it, because it's still being written. Thank you for staying all the way to the end. I hope this journey through the canyon left you with something worth thinking about. If it did, a like and a subscribe go a long way in helping this channel grow. Here's a question to take with you. 95% of the Grand Canyon's archaeological sites have never been surveyed. What do you think is still waiting to be found down there? I'd love to hear your guesses in the comments. Thank you for watching.